Okay, we move to the next talk, and we are going to listen to Valerie Gilchrist, who is an incoming PhD student at ULB, and she's going to talk about efficient supersingularity testing over FP and Seaside key validation. Valerie, you can start writing.
Thank you, Boris. So this is joint work I did with Gustavo and Ben when I was there this summer visiting for a little kind of internship thing. It's a paper I've already presented in Math Crypt, so I think a couple of you have seen it already. But I've made it new and exciting for you by changing the slide colors. So enjoy. This way. Right, so we're working kind of in the Seaside context. So I'm sure with this group, I don't really need to explain why Seaside is important or interesting. But we can recall, what the actual public key is in Seaside. So while we're working in Seaside, the public keys we're getting are these elements of FP, and these are corresponding to elliptic curves in Montgomery form. And so the question in the key validation is this corresponding curve supersingular? And one definition of supersingular is just that over FP that the curve will have p+1 points. And so this question is maybe not so easy to answer. Is it going to be supersingular or not? So we can start by looking at the algorithm that was originally introduced in the Seaside paper, which we refer to as the random point test. Basically, it just is looking for a point that has order p+1. So how it does this is it takes advantage of the Hasse interval, basically saying that if we can find a point of order that divides p+1 and that is at least the size 4 root p, then it must lie in this very particular interval, meaning it will have to be p+1. Kind of one drawback here is that you definitely need to know the factorization of p+1, which in Seaside is going to be of this very nice form. So in key validation, not really a problem. So how the algorithm itself works is we're going to start by taking a random point, and we're going to compute this kind of intermediary point, qi. So what we're computing is p+1 over li for one of these small primes dividing p+1. We're multiplying this scalar by p. Next, we're going to check that for each qi, first, that it's not 0, because otherwise it's not an interesting result. And second, that li times qi is equal to 0. If this is true, then we know that li is a divisor of the order of the point. We also want to check if li times qi is not 0, then actually the order of the point will not divide p+1. So the curve is not supersingular. We can terminate the algorithm right away. And basically, we're going to do this for enough of the small primes so that the product of these small primes will be at least 4 root p. And so in the case of Seaside 512, this corresponds to about 33 scalar multiplications, even when you start with like the largest possible li and work your way down. So memory-wise, it's quite nice, but efficiency-wise, there's some room for improvement. And so in fact, actually, they did improve the efficiency later on, but at a cost for memory. And this is what we refer to as the product tree test, because they use a product tree. So basically, they're noticing that you're doing a lot of the same scalar multiplications in the previous algorithm. And so they're going to store some of these in a tree and then search the tree breadth first. And so as I mentioned, this does give quite a speed up, but it's going to use a lot more memory than the previous. And so just a quick kind of recall of how a product tree kind of works is that our goal is to find upside down these leaves at the bottom. And so what we're going to do is we're going to start at the top and we're going to work our way down one of the branches. So kind of to get the first 2 leaves on the bottom, we're going to compute this intermediary value n over L1 times L2. We'll then multiply by L2 to get that first leaf. Once we've checked that it's a divisor, we can throw it away, go back up because we held on to this n over L1, L2. Now multiply that by L1 to get the other leaf, throw it away. And then we can go back, throw away this intermediary step, and then go down the other side of the tree. So because you're kind of holding on to one value per level of the tree, as the tree gets big, it's quite a bit of memory. Cool. So this one, yes. So I think on day 3 of an isogeny conference, maybe I can skip what an isogeny is, and also what the isogeny graph is. But basically for this next algorithm that we're looking at, we're only concerned with the 2 isogeny graph. And I'll comment on this a little bit later as to why, but it's basically just for simplicity. So this first test, we are looking at the isogeny graphs, as I mentioned. And so over FP, we notice that for all curves, supersingular or ordinary, we're going to get a volcano structure. So this is basically means we have this cycle at the top, and then we have these equally sized trees coming off of each of those nodes. And the cycle at the top is what we'll call the crater of the volcano, and then the nodes at the bottom, the leaves, are the floor. And so you also get this kind of notion of the height of the volcano, kind of how many levels are in those trees. And you can actually put a maximum bound on what that would be. And so where this gets different is that when you look over FP squared, the graphs of the supersingular curves are no longer volcanoes. They're actually 3 regular connected graphs, but the graphs of the ordinary curves still keep that volcano structure. So the idea of Sutherland's test, which was introduced in 2011, is to look at the graph of the curve over FP squared and try to determine whether it's a volcano or whether it's not a volcano, in which case the curve was supersingular. So how it does this is kind of starting at your curve, it's going to start 3 non-backtracking paths. And so the reason we need 3 of them is because if you're kind of in the middle here, we want to try to get to the bottom of the volcano. And so you might end up going up instead of down. So you need at least 2. And then also, if you happen to start in the crater, you might kind of end up going 2 directions around the crater. So you need definitely that 3rd one to start descending. And then once you start descending, you will continue descending. So we begin our 3 non-backtracking paths, and we're going to take log 2p + 1 steps through each path. We do this because that is the maximum height of the volcano. And so if we've taken this many steps in all of the paths and we have not hit the floor of the volcano, then you know you're in the supersingular graph. Obviously, if you hit the floor sooner, you can terminate the algorithm and know that you started at an ordinary curve. Yes, as I mentioned. So how we do this in practice is using something called modular polynomials. So this is the level 2 modular polynomial. It's already not super pretty, which is why we keep the 2 isogeny graphs only. But all we really care about these is that they have the very nice property that 2 curves will be 2 isogynous if and only if this polynomial evaluated at their J invariance is 0. So how we're going to look for neighbors in the graph is we're going to evaluate the 2-level modular polynomial at the J invariant of our starting curve, and then compute that over this polynomial ring with X. Oh, sorry. And so this is going to give us a cubic. And then once we factor this, we get the 3 roots. These are the 3 neighbors in the graph. At each step in each of the paths, we're going to divide through by the root of where we just were. And so this leaves us with a quadratic, which is even nicer to factor. And then you can choose either of the routes to continue down the path. Okay, sorry. If we do get to an irreducible polynomial, this means that we're at a leaf in the graph. And so, we've hit the floor of the volcano, we stop. If we don't hit an irreducible polynomial, then we're going to continue doing this log 2p + 1 times, which is the maximum height. And then after that, we can conclude that this was a supersingular graph. And so one thing worth noting, which I think is very nice, is that this is the only algorithm of the 3 that we'll look at today that gives a definitive proof of supersingularity. So that first algorithm we looked at, it will never categorize a supersingular curve as ordinary, but it might give an inconclusive answer. Whereas this one, you can be certain of whether it's supersingular or ordinary. So the first modification to the Seaside setting was actually given by Sutherland in his own paper, the original paper, which is assuming we are supersingular, then the FP portion of the volcano is actually going to be quite short. It's just going to be 2 levels, so those red dots. And so it's actually within 2 steps, you should be able to find one of those blue dots, which is going to be one of the FP squared neighbors. And so once you find one of those neighbors, you're necessarily descending, and so you can kind of abandon the other 2 paths. So because you're only following 1 path instead of 3, this gives about a 3 times speed up. Okay. Next are the modifications we did in our paper. So the first being kind of from the previous reasoning, we know that we're very quickly going to be in the FP squared portion of the volcano. So we only need to find a maximum bound on the FP squared portion, not also the FP portion. So this gives about a kind of a 1/2 difference. The second modification that we did has to do with how you take the steps in the graph. So instead of using modular polynomials, we compute an explicit 2 isogeny from each curve. And then basically this equates to like checking whether a discriminant is well defined. And then you can just kind of keep going with a sort of change of basis thing. Cool. So the third algorithm is due to Isogeny, and it uses something called division polynomials. So division polynomials are kind of derived from the group law, but again, what we care about is this very nice property that the mth division polynomial evaluated at a point will be 0 if and only if that point is in the m torsion of the curve. So if you might already know, there's this equivalent definition of supersingularity that says a curve is supersingular if and only if there is no p torsion over any extension field. So Isogeny kind of develops this supersingularity test that basically checks whether the pth division polynomial is going to be a constant polynomial or not. If it's a constant polynomial, there's no roots, meaning there's no point that would make this polynomial 0, in which case we're necessarily supersingular. So how he does this is he applies something called basic polynomial identity testing. And so he's going to take a random value and he's going to evaluate the polynomial at this value. So we're not computing the entire polynomial because that would be very difficult. We're just evaluating it at this point. If we get back a constant, it's either going to be 1 or -1, and you can kind of check what that should be. Because we're squared, it'll be 1. So if we get back a constant, we're in one of two cases. Either the polynomial itself is 1, in which case we're definitely supersingular, or we happen to choose a root of the polynomial, in which case, you don't, in which case it's not constant, so you wouldn't be supersingular, but you wouldn't know it from the result. Now, the odds that you choose a root are quite small. So if you do get a constant like of 1 value back, then you can say with probability 1 - 1 over 2p that it's supersingular. And so this algorithm does possibly categorize an ordinary curve as supersingular, but like probably not. So we're fine. So we only made one modification to this algorithm, but it's kind of a big one. So we noticed that computing scalar multiplication of a point can be written in terms of division polynomials. And so if you were to compute the multiplication by a scalar of a point in terms of the projective factor and projective coordinates, then the z value is going to be the division polynomial up to this projective factor. So essentially, if you can compute this projective factor, you can check whether the pth division polynomial was 1 or not. And so that's what we did. You apply one kind of iteration of a Montgomery ladder to get a multiplication by p. You compute what the projective factor should be, and then you can check whether the pth division polynomial was 1 or not. So quite remarkably, this costs only one scalar multiplication compared to the 33 from the random point test. And so comparing the three algorithms together, you get kind of in that last column, when you're checking ordinary curves, Sutherland performs very well because basically the algorithm terminates way sooner usually than the maximum. Versus when you're looking at supersingular curves, this is kind of the worst case for Sutherland. And so Isogeny ends up performing better. And so for this reason, we kind of suggest that for future implementations of Seaside, that the Isogeny test be used. That is all. Thank you.
Thank you, Valerie, for the very short and clear presentation. And any question? Yes.
Yeah, I was wondering if you looked at the square root value thing where they do take this product, they sort of compute the kernel polynomial a bit quicker by using a baby step, giant step thing. And it seems like you'd sort of use this instead of the product tree thing where you would be able to very quickly compute the right multiples of your point Q in some sense.
Oh, like for the first algorithm,
Yeah. Have you tried like maybe to see if that works, or is that easy to dismiss? Or
no, we didn't really work on the first algorithm at all. We kind of saw that there were these two other ones and tried to get them competitive with the first one. But yeah, you could try an improvement to the first one and maybe it'll outperform the others, but that wasn't something we looked at, no.
All right, thanks.
Another question? Yes.
I'm not sure if I have understood correctly, but the the division polynomial is impossible to compute, right? For you high values of p.
Like it's not
But yet
feasible. Yeah.
you are able to evaluate it at some point.
Yeah, so you can kind of like reduce as you go through the PS division polynomial. You don't have to like compute the whole thing and then plug it in. So you kind of have reductions as you go through the computation.
Oh, okay. So it cannot be used like reverse this somehow to produce supersingularity curves?
Oh, like
I assume not, because you need a point on which you evaluate the polynomial, right?
so you mean start
You need a point on the curve. Yeah, I think so. It doesn't work.
no, I wouldn't see how you can start with the division polynomials to get supersingular elliptic curves.
Yeah, no, it
No.
depends on the parameters of the curve. So you should leave the parameters
Yeah.
like free, and so you should have to you should construct the whole polynomial. It doesn't work. Okay, no, thank you.
No other question? Maybe I have one. Please, could you come back to the graph, the ordinary graph?
The volcano?
Yes. Yes, this one. No, yeah, this one. So you said that after 2 walks, if you get an FP square point, you continue with that point. So in the ordinary case, could it happen that you get an FP square curve which is still on the surface, for example?
In the what case? The ordinary?
Yeah.
So in the ordinary case, maybe like you won't find an FP squared neighbor so quickly. But then if that's the case, then you know you're ordinary and you stop.
Sorry, I don't get it well. So you said like if you start with the FP curve, then after 2 walks, you hit an FP square curve.
After 2 steps.
Yeah, then you continue with that one.
Yes.
But suppose that this FP curve was on the surface and the 2 walks that you did were on the surface, and can you like have an FP squared curve on the surface after 2 walks with?
No, so you'll do 2 steps in the 3 walks. And then at least one of the paths after 2 steps will find an FP squared. So you wouldn't find it on the surface.
Maybe I can ask this offline. I don't get it. Maybe. So if there is no other question, we thank the speaker again.